So this is a reaction you can see here is this one, yeah. So where's this one? This is the reaction like this, yes. This one with 5 substitute on methyl, 2 oxygen here. Yes, MCPBA acetic acid 120 degrees centigrade. You got this one's you get this one's, which is this one anhydride, and acetic anhydride 30 minutes. You get this one ester. So if we see this one structure first, how beautiful is this structure? This structure, yes. You go here, yes. You go here and run here, carbon double bond. You go here, 2 lines here. So you can jump here holding these 2 lines with your hands. NH, carbon, oxygen, double bond, NH, oxygen, 2 oxygen at 2, in 4 position, nitrogen, CH3. And where you get using MCPBA acetic acid 20 degrees centigrade, you get this one anhydride. So this is anhydride. What difference can you see here? What difference is? Difference is only anhydride and plus O. If you go back, this is a molecule same. Only what difference is? Difference is just using these reagents. You got this one anhydrides. Anhydride. So this is the reactions and using with acetic anhydride, yes. From here, acetic anhydride, if you use 30 minutes, you got this esters. What is going on? How these things happening? Amide not part of the game. Amide not part of the game. Then what is the game? What is amide? Amide is anything, carbon oxygen double bond, and then this is amide. Yes, this one, amide. You can see amide not part of the game. Then what? Then proton of methyl are very acidic. Okay, these protons, very acidic. Okay, these protons very acidic. Oh, that's really good. What they're going to do? Oh, there's great things we have discovered. We have found. Going to make funny. Yes, proton. Very acidic. Okay, let's see what happened then. You think about what happens. Okay, let's see what happens. Proton. We said. Next thing after that is in the mechanism. Acetic acid picks up a proton and forms Y is left is CH2. Is there any good nucleophile? Then acetic anhydrides in this reaction. If you see these reactions, we are asking, is there any good nucleophile? Yes. So, is there any good nucleophile? A question is there any nucleophile? Is there any nucleophile than acetic anhydride? Yes, N5 is a good nucleophile than acetic anhydride. Where is N5? This is N5. Yeah, so it is good nucleophile. So this role of this nitrogen is to extend the side chains. We are going to think about how this side chain is extended, and I will show you just now. So one idea is Claisen rearrangement. Claisen rearrangement. So Claisen rearrangement, what is? Claisen rearrangement is standard way of getting function. N is for directing the reaction. Okay, N is for directing the reaction directly. If we do not have this, we will not get 6 substituted product. Okay, so see what happens now. So this was the reaction, you can see. I won't repeat it, but I'll show you again. This region, yes, you have seen before, it's cute molecule, beautiful molecule, and using MCPBA, yes, acetic acid, 20 degrees centigrade, you get N oxide. Yes, you can see this is N oxide. So this is reaction. Yes, N oxide. Yes. So here we go. What happened after that? This is N oxide. Yes, and what happened? Using acetic anhydride, you get this ester. You can see this ester. Yes. So this reaction is like this. Okay. Yes. So this is one N oxide, and then what you get is this one. Okay. There's great thing. Oh, great thing happening. So going to talk about mechanism. Still the same thing, just this is a reaction, and thing happens like this. This is N plus, so negative. What happens with the acid? It forms CH2. It forms what? It forms CH2 negative, like this. So you can see one proton. Acetic acid has both one proton, no CH negative. And this is N plus and O negative, so we will see what is going to happen. You stay here between these lines. You keep your head away. Okay, who is winning molecule here? Who is going to secure a goal? Yes, we see who is. This guy comes, yes, this guy comes. Acetic anhydride. You can see 2 oxygen here. Yes, these are 2 oxygen. Yes, you look them. Okay. So 2 oxygen, yes, acetic anhydride molecule. Okay, 1 acetyl group, other between them is oxygen. What can happen? This can donate electron to 1 carbon of the acetic anhydride. So this is 1 carbon. So what happens then? These electrons then, these are a lone pair of oxygen comes here, and so what they do? They come here. And they provide a push here, and this one acetyl group leaves. So these are the things happening here. How beautiful is these things? How beautiful is this molecules? Can you see here? Yes, what is happening? This this electron providing push, oxygen is angry, getting oxygen. It has a lone pair say, I wanna give electron. I'm not even left behind. I'll secure a goal. And then when this gives electron, this is already 2 oxygen pulling electron. So when they get this electron from your oxygen, they steal the electron. They just run away. Electron for them is money. They just run away. Oh, money taken out. This was, it has a money say, I'm going to give. Oh, wow, how beautiful is. What happened then? What happened here? This is once we say one possibility. So this is one possibility that things happen like this. And what happened next? This is a leaving group here. You can see here. This one is a leaving group. This one, acetic anhydride. Yes, so we're talking about this one. You can see this one's a leaving group. When acetic anhydride, here I show you what happens. In this case, when this provided a push, what leaves from here is this one. Just leaves. This is a guy which leaves. This is a guy. Is a nutty guy having electron. You can still see they have electron, but it's a nutty guy has left. Is here a good nucleophile than acetic anhydride? So this is acetic anhydride nucleophile, but is there any good? Yes, N5. So we see what happens next. Now we're going to see what happens next. Yes, game is going to enter in tough situations. We see where goal goes, who secures the goals. Is a question here. Yes, we will say who secures the goal. Yes, so things happens. So here is something happening. Yes, what's this? I can show you 2 structures here. Yes, these 2 structures. You see what happens happening here. Just let's look first this one. Yes, oh, sorry, this one. Yes, so what is the same thing which we draw before? You can see when If it is like this, then what can happen? One possibility is, these electron attack here. So the first possibility I have shown you was this one. You just see this one. First possibility, this one. I mean, things happen like this. Another possibility, this one. Things like can happen like this. So who is providing push again? It's crazy guy. Who is crazy guy here? This was a crazy guy. Provide a electron. It has electron. It's going to give. It has force. It has energy. It's very energetic. You say, I'm going to give this electron. I don't want electron. Okay, pi bond also give electron. And this form bond. What will you get from here? So we go to next. This will form a if this provides electrons, like you see here, yes, this will be double bond, this will be single bond. Yes, this is a double bond. You can see this is single bond, no plus charge because electron have been provided here. So what happens here? This just it first form a bond here. Yes, you can see it has formed a bond here, but now it is not going to form a bond. It's going to leave like this. But see when it leaves, what fun is here? Is funny thing happening. Nitrogen provide a push, okay, but this oxygen, doesn't provide a push. There is scary from oxygen, no? Yes, what is does oxygen does a shortcut thing? Oxygen does a shortcut thing. It provides proton to carbon. It doesn't provide proton to this carbon. It provides proton here. It takes a proton from here. It doesn't form a bond with carbon, but form with this carbon. Why? It could be there is one oxygen. It's scary. This oxygen is a scary from that oxygen. You know what I mean? It has already oxygen. Yes. Oh, sorry. So this oxygen, yes, is scary from this one because it has a lone pair. So could be the repulsion here. And scary crowd is covered. So just go there, bum. And what happen if it's form the bond? Oxygen form a bond here, then what can happen? When it will leave, this will not separate because it is there. So it doesn't break, but it just do bum here. And what you got here is this one, straight this molecules like this. Means nitrogen oxygen bond, it just breaks. Oxygen form a bond here. This one oxygen comes here. It just jumps from here. See how good jumper is oxygen. See how good jumper is. Are you good jumper? This oxygen jumped here. One step jump. It jump here. Why it jumps? This carbon providing push. Say, I have energy I can give. Not you say, I am not weak. I have energy I can give electron. When oxygen gets sufficient energy, what happened? It jumps here on this carbon. It jumps next to the form bond next to the carbon. And oxygen here. Then oxygen has carbon, iron, CH3. You can see here, this is here. It's so easy reaction. If I go backward, I show you what happened. Just oxygen here jumping, you can see. Yes, it's providing oxygen just... is going to jump here, to secure a goal. It just jumped here and everything talks here and extended, and here it just formed the bond like this from the push. This is a crazy guy. I always provide a push. It provided a push here, this push goes here, this plus first finish, this oxygen form a bond like this, and you get this one. And then next thing this happens. One possibility was straight this one. Means instead of, but where this one goes is straight this one. Yes, and this just leaves. But then there will be problem with when O oxygen goes. So this is not the right mechanism. So right mechanism is this one. First carbon CH2 negative starts reaction, providing push, this double bond finish, this plus charge finish, this bond forms. And you can see these things happen first. This double bond is due to formation push from CH negative, and this double bond finish because electron comes here, no plus charge and oxygen double bond formation. But what happened here? Nitrogen again push from this double bond, nitrogen push and jumping here and moving everything here. This is the reaction. This is called enol tautomer. What it's called is called enol tautomer. So what do you think? What happened? Good thing happened? Yes. Enjoyable chemistry? Yes. How enjoyable is? How enjoyable is? I show you this enjoyable chemistry again. Right. This was the reaction. Yes. Enjoyable chemistry. Yes. So we're going to get this one. Going to get this one. Yes. From here. And now how? Wow. From this one. MCPBA. Yes. From MCPBA. And this one, yeah, wow, and this one and this one. Okay, the aromatic Claisen rearrangement is followed by re-aromatization. So this is one example. What's here? Can you think about what's happening here? Think about. This is source of electron, but usually, in the ring, these electrons not much available. But what is happening here? Can you think about? Tell me. This is also, electron. So if these electrons goes there, why it goes here? Question, oxygen providing a push. So if oxygen gives electron here and these electrons go there, this double bond will move here. So you will get like this. Because oxygen providing push, so you will get oxygen double bond, and this one will break, and this would be single bond, yes, and then this bond will be found here and here, yes, here and here. This will be not double bond, but next will be double bond. So you will get this one. Okay, so what happened? Just oxygen started the reaction by providing push. Arrow should be from oxygen to here, yes, and this double bond finish, this far on the bond here, this double bond go next, okay. But what is going to happen next after that? This is amazing now. This reaction is aromatic Claisen rearrangement followed by re-aromatization. And so we see what happens. There's funny thing happening here. I'm going to show you. Yes, very good thing. What happening? This is OH, just OH. And what was here? So this is proton, leaves. It's pulled by water, oxygen of the water, and this form a bond and this oxygen O negative then picks up a proton, and you will see OH and here double bond and this proton away. So this is the only thing which I can see here. Yes, it's no difference. Okay, so now we go further. See is anything. Right. So there are some other reactions with the same mechanisms. Yeah, so this is the reagent, yes, and this is something you can say is 2-methoxy group with carbon, yes. I will ask you to what can happen here. So this is first reagent, it's double bond. So source of electron here, just think about. And this is another reagent which is methoxy. They can easily leave, and nitrogen, to its 2-methyl. So what can happen? Do you think you can get this intermediate? And if you think yes, how? I show you all these 3 reactions in one line. Think about, tell me, what can happen? Think about. OH. Do you see here? I can see O, yes. And next to O, if I go like here, I can see double bond here. This is R1 and R2, so I can see R1, R2. So something happened here. This oxygen, is alcohol, but such alcohol which is a double bond as well. So alcohol did the reaction. So acidic alcohols, because it has a double bond, is more acidic than simple Keynes alcohols. So what happens? This oxygen what it does, this oxygen, what does? It's very good. Oxygen has a lone pair. So if you see this reaction, I show you three reactions together. Things happen here. You know, this oxygen, yes. So if you see this oxygen, yes. This oxygen just takes where? On this carbon-carbon double bond. So this oxygen takes on this carbon, okay? And all these leaves by protonation. And what you get here is double bond here just. So this form a double bond, and nitrogen is the same. So you can see two nitrogen, but what else you got here is double bond here. So how this double bond is formed? It's the same mechanism, but what happened after that? You think about how double bond formed, but I'm going to show what happened here. If you have here this one, I can see these are two nitrogen which was here. No, I can't see double bond, but I can see this oxygen here. Wow! And this next to oxygen was R1. No R1 there, so it means it just left away. This just jumped away, and this forms a bond here. So what happened in this case is this lone pair for push here and double bond, and these electrons go further at this position, not here, here, and these electron moves. You can see here. Can you see here? Yes. If I see this nitrogen, yes, and this oxygen providing push, so double bond, and these electron forming a bond here at this position, and this double bond moving here. So you have a single bond, double bond, R1. So this is the reaction which happened here. In the next reaction, butyl lithium, you know, using polar proton. So you have oxygen here. Yes. So this oxygen is going to do something. So butyl lithium, if you use, with this oxygen is a lithium now. Yes. So this is going to do something. Then what? Heat. If you heat and add some acid, what happened? Again, same thing happened. Lithium is not here, but is alcohol here. Lithium leaves. H replaces hydrogen, replaces this one. But something else is happening here. Again, same thing. Double bond, and these electron, you know, taking here. This electron moving here. You can see is same thing happening here. So, why are you talking about like this? Is this a comparison with your reaction? Is there? Yes, I think it's same comparisons. It's some not very much, but we just talking about, you know, reactions. We see what next reaction is. This is another reaction. Is so this is one thing. Is AMP is electron deficient, and what can happen if we use some reagent like acetic anhydride? Like something like this, no, acetic anhydride. This proton can be pulled easily, and these protons rich in electron can attack here, and this double bond will vanish. And what will you get then? You can get like this, means carbon double bond, yes, carbon double bond, and this form the bond here and NH. So we can get like this, yes. What can happen next if you have this one? Here I can see here in the next reaction. So this is fine, first thing, but what happened next here is this carbonyl, yes, this carbonyl, but something is happening here. I mean, it's forming a CC double bond. How double bond is formed? This is CH, so some electron coming from here, and they forming a double bond. Okay, you have formed a double bond, but how? Okay, the electron from the proton is removed by what? And those electrons left here, and you can see it's double bond formation. But now this double bond, yes, you can see this double bond. And you can reduce the bond with borohydride, yes. And further, what would happen if oxidizes? You can oxidize this ones. How this will form a double bond, and how this leaves? This is a question. I mean, how this leaves? Um, how can this leave? I can understand that this would provide a push, but how this carbonyl can leave? It can leave a protonation? No. Okay, this is a question now, how it can leave, but we said we got this one. We got another reaction, yes. Yeah, same kind of reaction, yes. So this is something, yes. What can you see here? What can you see here? Here, yes. It's the same thing first. In the beginning, you can see it's like, carbonyl and carbonyl and CH. This is from, the first our reagent which we used. I showed you here is, this one from this reagent. Yes, because usually we get this one, and double bond is this one, this no proton here. Okay, so double bond. This is the same thing again. But what happened next? What are you going to do? It could happen like this. What do you think? What do you think? So, means this OH, yes. O for me means this oxygen provided push here, and this proton leaves, and you means this form double bond and single bond. Yes, can it happen like this? Double bond and carbonyl? And you think so? So, if you say there's alcohol, okay, alcohol left by protonation. Yes, this can happen, but you can't leave all this carbon. To leave the carbon is not easy. So, but you are leaving here one carbon at all. So, are you? Yes, you're leaving this carbon, but to leave the carbon is not easy. So I don't see why this, how methanol, this is acetic acid is removed. It's not that easy. I mean, you can form a bond, but you can form a bond here, but removal of such a group with this next carbon bond is not easy. Okay, we don't know about this mechanism here. We need to think about further, but we go further whether we have something else. This was one reaction. Yes, we did using this acetal. Yes. Now difference is this is acetal, but before we used to have here methyl. This is acetal. This is the only difference. So we will get the same thing with the same acetyl group. At the end, you can see is ethoxy here. Yes, and this is CH2 and NR. R could be anything. And same condition, here this solvent and a dimethylformamide and using NER, and we will get NER at this position. This is a CH3, but here would be R, and finally okay, this would be R, NER here, yes, and CH3 OH3, but this is wrong. Yes, if ethyl here, it should be ethyl here. So this is OH, yes, and using our standard condition hydrogenation, palladium, water, DMF, methanol, ethyl acetate, we will get R here. And these are the three regions we can use, and at ortho position, meta position, and ortho position, you can see these are the R, yes, and double bond. Okay. So we do the reaction now and see what happens. So this is the reaction is happening, okay? The first reagent, this one, which you have seen many times, using this dimethylformamide and using this acetal, you're going to get this one. This is ortho position nitrogen, and then next nitrogen is double bond, alternative double bond, and ethoxy, ethyl group here, CH2 here. Okay, we go to next reaction. Now we did some reaction which was using this one, POCl3 and triethylamine. We were supposing that we will get chlorinated product, which was this one, but we didn't get. We will think about this one later. Yes, but this is what we were supposed to get. Yes. Okay. So but we didn't get here, but you can see here is this one, nitrogen double bond, and no oxygen here. No oxygen should left. This is chlorination of the reaction. First we use POCl3, yes, POCl3, but now we're going to use something else. This is POCl3 for chlorination, chlorinate this product, okay? Now we're going to use something else. What's something else? Using this one, yes, and this is gaseous reagent. So you were asking me the structure of gaseous reagent. This is structure. Can you think about how to draw the structure? It's easy. You little bit dance here. This carbon and other carbon, two carbon. So dancing on these two carbon, between them is a double bond. Okay. The upper carbon has two methyl group. So you go here, CH3, three roses in your hand, catch green, grass here, dance little bit here, and you go CH3, very nice, CH3, you three apple, three roses here, three apple, whatever is, but it's very beautiful green trees. You stand here, you hold them with three, you kiss them, these three hydrogen atoms, and then you come here. You are very, very good. This is a bridge, two lines you can see. So between two carbon is what? Is two lines, two bridge. You run them, you run away there, whatever you do, but when you go next, you won't see anything here except two carbon. Is very beautiful. But here is chlorine, which you need, and next is nitrogen. What is next? Next to is nitrogen, and next to nitrogen is again 2-methyl. So this is structure of gaseous reagents. Okay, gaseous reagent structure is like this. Is how amazing is this structure? Is very, very good structure. Yes, you can see gaseous reagent structure. How this is two carbon. You run here, you run here, you run here, you run here between this carbon, and 2-methyl. You can't go further. Here one chloride. Hold this one chlorine in your hand. This is what you got. This is what you want. Chlorination. And when you go next is just one nitrogen. So beautiful nitrogen. It's more beautiful. The rose is amazing molecule. And then next to methyl. So you have 2-methyl next to carbon, 2-methyl next to nitrogen, and between them is just 2 carbon and 1 chlorine. And total carbon 2 here, and 1 this one, 2 this one, 2 to 4 to 6, 1 nitrogen, 1 chlorine. This is what gaseous reagent is. You're going to expect this one. I hope you remember the formula of gaseous reagent, which is this one. Okay? I hope. Yes. Next. For chlorination, we use other reagents. This is thionyl chloride, and this is diisopropyl and ethylamines. So this is an amine, single amine, and thionyl chloride, and you can get this one's chloro product, dichloro. Other thing, this is one molecules, yes, same molecules, and this is a base. This is base. You can see it's base, yes, DBU. So this base show you when this is amine, yes, benzylamine. What is benzylamine? Benzylamine is usually 6 member and then CH2 and 10 NH2. This is called benzylamines, okay? Benzylamine. And this is DBU. What's DBU here? What means, how many member this one? 1, 2, 3, 4, 5, and 2, 7. So if I start from here, 1, yes, 1, 2, 3, 4, 5, and 2, 7. This is 7 member, and then 6 member, and meta position is nitrogen. It's double bond. So total, if I start from nitrogen, 1, 2, 3, 4, 5, 6, 7. Total 7 member. This is you can see this is what is this? This is catalyst. If you remember the structure, PF6, phosphorus, fluorine 6, so 1 fluorine more, so is negative charge because phosphorus bound with only 5 without any charge. Phosphorus plus 5 valency. Here again, this is phosphorus. Phosphorus is a crazy guy. Here, holding 5 female fluorines, and it should hold 5, but it is holding one more, and here it is again holding something. What? 2 dimethyl? 1 here. Wow. 1 here. 1 here. So total 3 is not satisfied. Yes. 1 here. Bond 4. So 2 dimethyl, 1 oxygen. But still it doesn't want more. So it is plus charge. Still have a plus charge, because it can make another bond. 1, 2, 3. In this case, it's using 3 valency. It has given 1 more electron, so this is plus charge. And what is this? This is 6 member. It's very easy. And next is 3 nitrogen. Just nothing at all. Nitrogen. These are forming double bond, just like diazo, and this is another nitrogen. So just 3 nitrogen, and this nitrogen form a bond here. This one's with phosphorus, which has 3 dimethyl, and this is a reagent, and we were going to supposed to get this one, CH2 and the benzyl at both positions, NH1 proton less from benzylamine here, and double bond, and here double bond. So this was we were supposed to get. This is another reagent, same reagent, but another catalyst. So what is this? Think about. This is T3P. T3P, yes. Yes. First was BOP. B-O-P. BOP. This is T3P, and T3P is ammonia gas and hindered base against dimethyls 2 and 1 ethyls. You can see here, this is T3P. T3P. How many phosphorus? You see here how many phosphorus. You remember in the first structure what was? Can you tell me just now? I'm asking you now first structure. Yes, if you think about a little bit, this was a structure. Yes, a catalyst structure I'm talking about. Phosphorus. Yes, phosphorus. Okay, and with phosphorus, 1 N 2-methyl, another N 2-methyl, another N 10-methyl, another oxygen, and 1 more bond formation. So plus charge, and another was 3 just nitrogen, 6 member ring, and PFC. So this was structure, but here this is phosphorus again. Crazy guy, everywhere phosphorus, but it's forming double bond now. Phosphorus tried to forming too many bonds, because before it forms 3 bonds with nitrogen and 2-methyl, and 3 bonds with you. I'll show you back. Here what they did, phosphorus forms 3 bonds with nitrogen, yes, and having 2-methyl. But here what is phosphorus? Again phosphorus T3P forming a bond, but how many? Wow, it's forming a bond with methyl just. So just 1 methyl. It's say 1 methyl enough. But here you say is isopropyl, but why here just ethyl? I will check. I think the wrong structure. It should be all isopropyls. Yes, so this is phosphorus forming 1 bond with double bond with oxygen. Yes, and other bond just with oxygen, which is in between all phosphorus. So 1 oxygen in between these 2 phosphorus. So this is a bridge. Phosphorus. You can jump here, stay here, go here, jump here. If you want to go here, it's 2 double way. You can come and go back, and you want to go here, just 2 things, 2 branches. So with phosphorus, 2 branches on all sides. This is wrong. It's 2 branches on all sides, but 1 oxygen with every phosphorus and 1 oxygen is in between. This is T3P. And if you use ammonia gas, you're supposed to get this one. This is wrong structure. It should be double bond here, because double bond here should be double bond here either. Okay, sorry for wrong structure. Yes. So this is end. Well done. End. Whoa.